Hello, everyone who joined us in this session. Thanks for coming. As you remember, yesterday we talked about commutative Banach algebras, and we start exactly this special topic because before we just consider all Banach algebras, not necessarily commutative. But yesterday we started commutative ones, and I just give you the definition of ideals, maximal ideals. And I told you there is a bijection between the elements in the character space and also the maximal ideals of A. And now I want to exactly say this relation. But before that, we need to know quotient algebras. I think everybody in functional analysis knows this subject for Banach spaces. When we have a Banach space and a closed subspace of that Banach space, with quotient norm, we have a Banach space. And now we consider Banach algebra and we want to make it a Banach algebra. That's why we consider closed ideals. Okay, let's start with quotient algebras. Suppose that I is a closed ideal of A of a Banach algebra, commutative, of course. A means a commutative Banach algebra. Yesterday I told you commutative Banach algebra. A and A over A is the algebra of all cosets of I in A. Algebra of all cosets of I with the quotient norm. Which is defined as follows: norm of A plus I is the infimum of norm of A plus B when infimum is all over elements in I. And usually we use P of A instead of A plus I, and P is a quotient map from A onto the quotient space. And P from A to A over A is the quotient map. From functional analysis, we know that this is with this norm is a Banach space. And we know let's sit here, Banach algebra. We know that is a Banach space with quotient norm. I want to make it a Banach algebra, Banach space. To make it Banach algebra, first of all, I need to define a multiplication. We define multiplication as follows. P of A multiplied by P of B is a natural way, just we should define P of A, B for each A and B. And of course, this definition will define, for example, if P of A is equal to P of A prime, P of B is equal to P of A prime, and so A minus A prime should be in I, and B minus B prime should be in I. And for example, AB minus prime B prime, let's add and subtract, for example, all B prime. So we have A, B minus B prime plus B prime, A minus A prime. And this is in I, so it is in I. And this one is also in I. And finally, this element is in I. So we can say that P of A and B is equal to P of prime, prime. So the multiplication is well defined. And it's enough to show that the norm is algebraic norm. It means that it's satisfying submultiplicativity, and that's enough. And of course, P of identity element is 1. It's obvious that with this definition of multiplication, P of E is the identity element. Okay. So we want to show that P of B, it has most P of A, P of B. This is, I want to show it for each A and B in A. Okay, it's usual. It's common when, for example, we want to show that T is less than or equal to S. Instead of this, we show that for each epsilon, T is less than or equal to S plus epsilon, especially when we have epsilon infimum or supremum, because we can use better from the definition of supremum and infimum. Anyway, that's why I enter epsilon here. And because of definition of quotient norm, we can say that there exists a prime in I such that norm of A plus A prime is less than norm of P of A plus epsilon, because this is the greatest lower bound. With epsilon, it's a lower bound. That's why we can find A prime. And similarly for P of B, let's consider this multiplication. We have AB plus A prime E of A prime and also A prime vector. There are elements in I and also this Y and this Y, and I is an ideal, so this is in I. And according to the definition of quotient norm, we can say that norm of P of, let's see, write it down. We can say that P of AB is at most, because the infimum of such norm of such element. So AB plus this, or I put here this one instead of this. And from the above relation, we have this is less than the norm of P of A plus epsilon. Of course, this is a norm in A, and we know that A is Banach algebra, so we have the algebraic norm. First of all, I use algebraic norm, and then I use this one. But I wrote the final guy. Anyway. And since epsilon was arbitrary, let epsilon goes to 0. So we have P of AB. It has most P of A, norm of P of B. So we have submultiplicativity of the norm. And also, from this definition, we can say that P of E at least 1. On the other hand, we know that the quotient map is always continuous and norm decreasing. It's enough to consider element B 0, and we can say that norm of P of A is at most norm of A. So it's less than norm of E, which is 1, and then norm of P of E is 1. Hence, quotient. Our quotient space we know before as a quotient space is a Banach algebra. We say it's a quotient algebra. And now we want to make relation, as I told you, between the elements in character space and the maximal ideals of A. And I said in this theorem, which has some parts. Okay, and okay. The first one, each maximal ideal of A is the form of kernel of one homomorphism or one element in character space. Okay. Is of the form of the kernel of some B in M of A. And the second part shows that the converse is also true. The kernel of each homomorphism is the maximal ideal of A. If B in M of A, then kernel of B is the maximal ideal of A. And the third part says that it makes the detection I told you, but the other parts like more information concerning invertibility of elements. This theorem is also very handy in the next part, so I give it also and start. Second, we had one theorem with a star, and this is the second one. A is invertible if and only if for each P in M of A, P of A is not 0. Or now I say it with maximal ideals or ideals. I doesn't belong in any proper ideal. Or in other words, A lies no proper ideal of A. And the last part, lambda in a spectrum of A, if and only if lambda is the form of P of A for some P in M of A. In other words, it shows that spectrum of A is the phi of A when phi in M of A. Okay, for the first part, it shows that each maximal ideal is the kernel of some homomorphism. Imagine, for example, maximal ideal, put it M. You know that actually I show that A over M is isomorphic to C, and up to an isomorphism, we can say that the P, the quotient map, is the phi we were looking for. And, you know, when we have maximal ideas, we have A over M, quotient algebra is just C. And so I prove it. And you know that M is a maximal ideal, and so it's closed, and this quotient algebra is well defined. And to show that it's just C, I use Gelfand major theorem, and I show that each non-zero element here is invertible. And finally, it's isometrically isomorphic to C. Okay. Let's A in A minus M and put J as an I, B plus M. The algebraic ideal generated by A and M. And M, I mean the maximal ideal I added in the statement. B in A, M in M. Then J contains M because it's enough to consider B 0, and then we have it. And of course, it's a subalgebra of even ideal. Ideal of A. This is ideal. It's easy to check that. And this is proper. No. It's not proper. Sorry. Here is proper because A in J, but not in M. Why A is in J? Because it's enough to consider B, E, and M 0, and then A is in J. But M is maximal ideal, so J cannot be a proper ideal. So we have J is A. And in particular, E also is in J. When E is in J, it means that there exists P in A, M in M, such that E is AB plus M. And then P of E is P of A plus P of B plus 0, because P of M is 0. It shows that P of A is invertible because P of E, the identity or unit element of quotient algebra. Okay. So each non-zero element in the quotient algebra A over M is invertible from Gelfand major theorem. We can say that it's just C. So by the Gelfand major theorem, Gelfand major said that each the only Banach algebra which is Lipschitz algebra is C. AMOM is C. Okay, or let's, for example, J, this isomorphism, define. This is an isometric isomorphism. Here now it's defined phi J O P, which is in the M of A, and which is in M of A, and kernel of phi is just M. It's kernel of P. It's an isomorphism. Okay, and the second part, the converse of the first part, I want to show that each kernel of each character is maximal ideal. Of course, if phi in M of A, then kernel of phi because it's a linear and also preserve multiplication. So kernel would be an ideal. Kernel of phi, because kernel of phi is just phi minus 0 is an ideal of A, which is maximal because it has codimension 1. Why it has codimension 1 is clear because A, for example, like A minus phi of AE plus phi of AE. A can be written like this, and this is element in the kernel of phi, and so codimension is just generated by E. That's why we can say that codimension is 1. The next part, um, if A is invertible, of course, this I said this part before. For each phi of M of A, that's because it's not very long, I prefer to write it here. 1 is phi of E, and it can be considered as A multiplied by A inverse. Then phi of E is not 0. For the converse, it's this part. And for the converse, if A is not invertible, then the algebraic ideal generated by A, I mean that AB being A, is a proper ideal of A. And I told you yesterday, which is contained in a maximal ideal of A. Like N. By the first part, we can say so there exists phi in M of A such that N is the kernel of phi. So I is a subset of M, so I is a subset of kernel of phi. And then phi of A is I in I, so phi of A is 0. So the um, we prove that C from the previous part is really easy because if A is invertible, so it cannot be any maximal ideal. And if, for example, it's any proper ideal, then each proper ideal can be contained in a maximal ideal, and so it's not true. And for the converse, of course, we can use again the previous part. And for the last part, it's enough to consider, for example, part C for A minus E instead of A. Let's write the last part. D, it's clear by the previous part, of course. And E, you know that a spectrum of A is a set of lambda in C such that lambda E minus A is not invertible. According to the part B, if it's not invertible, it means that there exists phi in M of A such that phi of this element is 0. In other words, it means that because phi is linear, we can say that phi of A is lambda. So lambda is the form of phi of A, and we can go back if lambda is phi of A. So it means that phi at this element is 0. According to part C, this is not invertible. So it's exactly phi of, instead of lambda, we can write phi of A when phi in M of A. Just and this completes the proof. And especially its theorem shows that each maximal ideal of A is, because we know that uh, we know that the maximal ideal of A is non-empty because we can just consider an invertible element and use this, and we know that each proper ideal is contained in a maximal ideal, and then we use this one. We can obtain an element in kernel of phi. So in this theorem, it especially shows that maximal ideal of each commutative Banach algebra is non-empty, and it's feature of commutative Banach algebras. If, for example, without commutativity, maybe the character space is empty. For example, there is an example in the Lasko book and L1 of, I think, unit interval and commutative Banach algebra without any character. And for non-commutative but unital, I told you Mn, of course, when n is greater than 2. The maximal ideal is empty. But for commutative, no. And they're very useful in commutative case because it makes to just consider Banach algebras of C of X instead of each Banach algebra which is commutative, which is actually Gelfand representation. And I want to tell you now. First, I want to, we know that R of A is the supremum of element in a spectrum. From this theorem, we can say that R of A in the commutative is very efficient because it's a phi of A when phi in M of S. Yes. And because I want to tell you in the exercise, but before that, I say corollary. If, of course, we had it before in non-commutative case, and I told you in commutative case, we can obtain it easier. Then phi is continuous and norm of phi is 1. Because if A in A, and let's A in A with norm of E is at most 1, we know that phi of A is in the spectrum of A, and so phi of A, we know that the spectrum is bounded by norm of A, and which is less than 1. Then norm of phi at most 1, and since phi of E is 1, we infer that norm is 1. And the other corollary, which is leave it as an is the exercise to show that in commutative case, we can say that R of A plus B is at most R of A plus R of B. It means that spectral radius has subadditivity property or subadditivity or and R of AB is at most R of A, R of B. And also spectral radius has submultiplicative property for each A and B in A. But in general, a spectral radius is not subadditive or, of course, is not submultiplicative in a non-commutative case. For example, check for this example. Let's A is M2 of C, A is this matrix, and B this one. And you can show that this inequalities aren't true here for non-commutative. And this is, of course, this is a key for because this is a key for commutative case. Now we are ready to say Gelfand representation for commutative Banach algebras. Okay. Gelfand transform for each A in A, we define the Gelfand transform of A by this. This is a map from M of A, which we know that this is non-empty, from C, which takes phi the natural way to phi of A, and puts A hat the set of all transformation of A. We want to define a topology on M of A, which is called with Gelfand topology. Actually, the topology which makes the weak topology, weakest topology, which makes every A hat be continuous, or in other words, the weak topology induced by A hat is called the Gelfand topology, and we consider this topology for M of A. Okay. The Gelfand topology on M of A is the weak topology induced by A hat. It means that this is the weakest topology on M of A, which make each A hat continuous. So clearly, A hat is a subset of M of A. Of course, it means that the algebra of all continuous function on M of A. Of course, we had before C of X, but X was compact Hausdorff, but we don't know if with Gelfand topology is compact solve. That's why I just write it here. It's the algebra of, anyway, but this is an algebra with point-wise operations. In any way, doesn't matter. Algebra of all continuous complex valued functions on M of A. And the Gelfand transform the Gelfand transform of A as an algebra, I mean. The Gelfand transform of A is the map. Because I want to make it in, use it in next theorem, I prefer to put a name for it. From A to A hat, this map A takes to A hat. It's a map from, which is a map from A onto surjective from A to A hat. And since there exists, as I told you, okay, because of this example, this theorem, which is one-to-one correspondence between the elements in M of A and the set of maximal ideas. So sometimes M of A character space in the commutative case is usually called with the maximal ideal space of A. And let's say something. This sum is exactly unique. That's why I said bijection. Because you know that it's very easy exercise. If you have two linear elements in M of A with the same kernel, they should be definitely the same characters. It's really easy to do. I mean that this is really huge. So because of this theorem, M of A in commutative case is usually called the maximal ideal of the maximal ideal space of A. That's why I use M instead of other notation. I prefer to use M of A. M of A with the Gelfand topology is called the maximal ideal of A. Sorry, ideal space of A. And the final definition, this is an algebraic definition, radical of A. I think you've seen it before, which is the intersection of maximal ideals of A. The radical of A is the intersection of all maximal ideals of A. And noted by radical of A. So radical of A, according to this theorem, we just write it, we can say that intersection of maximal ideas or intersection of kernel of V when V in the character space of A. And now I want to say Gelfand representation theorem. Just I want to say something. As you see, both M of A is a subset of B of A star and especially A star. And so we have a weakest star topology here. And you know that weakest star topology is A topology on A star. It means that the weakest topology on which elements like a T from A star to C, this takes P to P of A is continuous. A hat is like this, but A hat just consider the restriction on M of A. So it's easy to see that exactly Gelfand topology, and before that, because star topology, it's exactly the weakest topology on A star that makes each A hat continuous. And the Gelfand topology is the weakest topology that makes each A hat is continuous, just here. So we can say that Gelfand topology is relative weakest star topology. In other words, the restriction of weakest star topology on M of A is Gelfand topology. And look, because it's really easy to check that each local base here we consider, it can be just consider with intersection with M of A will be a local base for here. The Gelfand topology is a relative weakest topology. Now I want to say that Gelfand representation theorem and other parts, of course, with other parts. The first one says that M of A, the Gelfand topology or weakest star topology, doesn't matter, is a compact surface space. The second part says that the Gelfand transform A actually is okay. Actually, this map is a let me fix it. Hope it works. Is homomorphism from A onto A hat. Okay. Okay. The Gelfand transform. I call it gamma. Is a homomorphism of A onto onto A hat. Subalgebra of C of M of A. Onto subalgebra of A hat. Subalgebra A hat of C of M of A, whose kernel is radical of A, whose kernel or null space is radical of A, and also the Gelfand transform is an isomorphism if and only if, because we only don't have, this is surjective, but is isomorphism, it means that we have injectivity, and so kernel of gamma should be 0, kernel is radical of A, and so we expect to have A is semisimple. And the last part, which is very easy from this theorem, and also the second star theorem, for each A in A hat of M of A is a spectrum of A. We just did before in the last part of the previous theorem. And so supremum norm of A hat is R of A, and this is at most norm of A. We know that. Moreover, A in radical of A, if and only if R of A is 0. Um, for the first part, we know that M of A is a subset of A star, and even in the closed unit wall, even in the unit sphere. Just here, we had it, the theorem. B of A star, it means the dual space of B in AS. I mean that this is phi of A star, and the norm of phi is at most 1. This is. And we know that this is VK star. With VK star topology is, of course, VK star topology is Hausdorff. And Gelfand topology also, because it's relative VK star topology. Apart from this, even because A hat separate the points of A and A, weak topology induced by A hat will be Hausdorff. But anyway, this is Hausdorff. It will be Hausdorff because it's just with relative topology, and also this is compact with Banach theorem, and so the space is compact. Hausdorff, it's enough to show that this is a weakest star closed subset of P of a star. And in that case, we can say that it will be compact. We know that this and B of a star with weakest star topology is weakest star Hausdorff, and weakest star compact. Weakest star compact by thanks to Banach theorem. By the Banach theorem. So we need to show that just M of A is a closed subset of P of A star. In that case, it's we can conclude that M of A itself is compact. It's enough to show that M of A is weak star compact? Is weak star closed? Sorry. Closed is a weak star closed subset of M of A. So let's, for this paper, let Phi alpha be a net in M of A such that Phi alpha goes to phi in B of A star. We need to show that phi is an M of A, and for this purpose, it's enough to show that phi preserve a multiplication because linearity, and we have other things, linearity of course, just and multiplication, and it's preserved multiplication. Okay, it means that we have it in weak star topology, or yes, weak star topology, and then it means that for each A, phi alpha A goes to phi alpha A, sorry, phi of A, and it works for each element, so phi alpha B goes to phi of B, phi alpha AB goes to phi AB because of weak star topology, because I told you yesterday. So we have it. They're just elements in C. So phi alpha A, phi alpha B goes to phi A, phi B. Phi alpha is a homomorphism, so it is phi alpha AB. On the other hand, phi alpha AB goes to phi AB, the limit is unique, so we have phi of AB is equal to phi A times phi of B. And let's write it here. From all these parts, we can say that phi alpha, phi of AB is equal to phi of A, phi of B, because the limit is unique. And the second part is really easy to check. B. For example, let A, lambda A and B in A. So lambda A, Gelfand transform of this function at phi. Phi is an element in A star. It's M of A, sorry, M of A. So we have, according to the definition of Gelfand transform, we have lambda A plus B, and phi is a linear functional. Lambda phi of A plus phi of B, rewrite it again with hat. And we can write it lambda A hat plus B hat at phi. Phi is an element in M of A. Then we have it. Then this function should be the same. I mean that hat of lambda A plus B is lambda A hat plus B hat, or gamma of lambda AB is lambda gamma of A plus gamma of B. So Gelfand transform is an homomorphism. And of course, kernel is radical of A. It's clear because kernel of gamma, it means that A in A such that gamma of A is 0. Gamma of A, it means A hat. A hat as a function is 0. It means that For each phi, we have phi of A is 0. For each phi of M of A, it's just intersection of kernel of phi, and we know that this is just radical of A. And so kernel is gamma is an isomorphism, gamma isomorphism, if and only if, because we have subjectivity, linearity, and homomorphism, just we need injectivity, if and only if kernel of gamma is 0, and kernel of gamma is just radical of A, and it means that A is semi-simple. And of course, the last part is really easy to check that. Of course, we had something like this, but without knowing the notation of A hat, just here we use notation of A hat. R of A is the first thing I wrote after the first theorem here. So see here, but you can check it yourself, please. Really have to cover some things, and I want to be on time. On the other hand, so anyway. I want to give an example and determine maximal of ideal space of little L1. We had the first session, one of our example. Before that, I say a definition and a proposition, and then I characterize all maximal ideals of L1 or character space. If S is a subset of A, we say that A is generated by S if the linear combinations of products of elements of A, elements of S are dense in A. Linear combinations of products of elements of S is dense in A. I mean that the algebraic ideal we can consider here is by S is algebraic, sorry, subalgebra we can consider here is dense in A. And a very simple proposition. If A in A, then A hat, we know that it comes from M of A to see what is a homeomorphism from M of A, because I want to make it surjection. So I have to consider spectrum onto a spectrum, because you know that just the last part of the previous theorem, A hat of M of A is the, because A hat of M of A, phi of A, and it's the range of A hat is just elements of in a spectrum. In spectrum, on a spectrum of A. In each of the following cases. First one, if A is generated by just A and E and A or A is inversible, yes, and A is generated by A and A inverse. It means that each element character is determined by their action on E and A and E, and here A and A inverse. We put two parts together, and we know A hat from M of A onto a spectrum, which takes phi to phi of A. According to the Gelfand topology, it continues, and range of M of A hat is the previous theorem is the spectrum of A, so it's continuous surjection. It's enough to show that it's injective. And of course, when we show that it's injective, it will be a bijection between these two spaces, but it's compact. This is of course compact, but Hausdorff because we need Hausdorff here. And anyway, the converse is will be continuous, and finally we have a homeomorphism. So I mean that it's enough to show that this is A hat is injective. Thanks to compactness, we can obtain the continuity of inverse. It's enough to show that, sufficient to show that, A hat is injective. Okay. Let phi and psi in M of A such that A hat of phi is A hat of psi. For the first part, it's clear because each element can be uniform limit of, not uniform, of course, the limit of polynomials by E and A. And the second part, of course, is not difficult because if in A inverse, then it's also true for, which means that phi of A is equal to psi of A. Then phi of A inverse is, we know that it is inverse of phi of E, and phi of A is psi of A inverse, and psi is also a homomorphism, homomorphism character, and so we get phi of A inverse is psi of A inverse. Each element is the limit of linear combination of products of elements in S, just here A and E, and this one A and A inverse. Because of linearity and of course being homomorphism, preserve products, and for this part, continuity of elements in M of A, we can say that phi is equal to psi. Since B and psi are continuous homomorphism, in M of A. Okay, true, but then P is equal to psi. Now I want to determine maximal ideal space of or character space of L1. M of L1, just I want to say that homeomorphic with T, of course, the unit circle. Lambda in C, absolute value of lambda is 1. Anyway, wait. You know that for each K in Z defined element in L1, I want to say that actually L1 is generated by E and one of the elements which is invertible. Actually, the second part, of course, the previous thing. For this purpose, I introduce this function here. Delta K means element in L1 such that n entry is 1 if n is k and otherwise is 0. Just an entry is 1, sorry, in k is 1 and the other parenthesis is 0. And so it's easy to see that delta m is the convolution is exactly delta power m plus n. And delta with induction, you can see that this is convolution of delta 1 k times and or delta minus k is of course convolution of delta inverse. Delta inverse. And it's actually inverse of delta 1 because delta 1 star delta minus 1 is delta 0, which is exactly unit element. And by this notation, each A in L1 can be written like this: sigma an delta n, and from minus infinity to infinity. And then L1 is generated by delta 1 and in its inverse. Exactly like the second case. And so it's enough to determine spectrum of delta 1, I mean. Let's be in M of A and put lambda as the phi of delta 1. Absolute value of lambda is the absolute value of phi of delta 1. It's at most norm of phi, the operator norm of delta 1. Norm of phi we just before it's 1 and norm of delta 1 is of course in one element is 1 and the other 0, and so this is 1. And lambda inverse is just exactly phi of delta inverse because they are inverse of each other. We know that it's 1 over phi of delta. Phi of A and A inverse, they are just over of each other. The multiplication is 1. And so this is, again, this is 1. Norm of this element in just when n is minus 1 is 1 and the other part is 0. So this is just 1. And so we get the absolute value of lambda is 1, lambda in T. And for each A is of the form of an delta n. Phi of A is because phi is homomorphism and also continuous is n phi of delta 1 power n an. This is lambda n. So phi of each element can be determined by this lambda. It's the second part. And then A hat, of course, delta 1 hat from M of L1 to unit circle is a homomorphism. From the previous proposition. And so M of L1 is homomorphic to T. And from this example, we can obtain a nice result in Fourier algebras. I like to mention it here because we can obtain it by this characterization of maximal ideal space of L1 and also the second star theorem I just said at the beginning of the class. So I like to mention it here, which is Wiener's lemma concerning absolute convergence of Fourier series. Wiener's lemma if f of actually each lambda in T can be written like E over I theta. If I use this notation here, I have sigma an E power I n theta. Okay, because I want to use this notation. If f of E I theta is sigma am E I n theta with absolute value of an is finite and f never vanishes. It means that for each theta, f of ei theta is not 0, or 0 set of f is empty. Then 1 over f is well defined at each element in unit circle, and it is Bn Ein theta with sequence like Bn such that the absolute value, sigma absolute value of Bn is finite. Actually, from this statement, we can say that f is a hat where a hat is a is an in L1. And since f never vanishes from exactly the third part of the star theorem, we can say that it will be invertible. Since f never vanishes, it's invertible because for each element in character space, we have a hat is not zero, a hat of phi of a, sorry. F is A is invertible put B as the inverse of A. Then this is just B hat. Okay, if I say a little fast because I want to cover all things. The next theorem, which is nice, I told you yesterday, just one case, the algebra is not necessarily commutative, but it's exactly this point. If T from A to B is a homomorphism of a not necessarily commutative A, Banach algebra A into a semisimple commutative Banach algebra B, then T is continuous. This theorem puts in the automatic continuity theory, which is very popular research area in Banach algebras. For example, one of references, Dell's book, some part is just devoted to automatic continuity, and this is just a special case of theorems in this relation. Okay. To show that it is continuous, equivalently, we can show that because they are Banach, we can show that the graph is closed. I use the closed graph theorem. So for this purpose, let's AN is sequence in a sequence in A such that AN goes to A and T of AN goes to B. By the closed graph theorem, it's enough to show that B is T of A. And because it's semi-simple, in other words, we have to show that B minus T of A is 0. B is semi-simple, it's in which 0 is also radical of A. So it's enough to show that B minus T of A is in radical of A. And radical of A is the kernel of Gelfand transform. And so it's enough to show that for each psi in M of B, psi of B minus T of A is 0. That's why I insert psi in M of A. Let's psi in M of B and define phi as psi or T from A to C. If it's 0, it's continuous. If it's not 0, it's an element in character space of A, and we know that it's the elements in character space is automatically continuous. And so, anyway, V is continuous, and I told the reason. Then, so, psi or T of AN, AN goes to A, goes to psi or T of A. This is psi of T of A, and this is psi of T of AN. But we know that T of AN goes to B, and psi of Tn goes to psi of B. So on the other hand, it goes to psi of B. Okay, the limit should be unique. So it shows that okay, let's write it here. And psi of T AN goes to psi of B because it's psi of T of AN, and hence we just write it here. Psi of T of A should be psi of B, and psi of T of A minus B is 0 for each element in character space of M of B. So it's in radical of A, radical of is semi-simple, so radical of is 0. AN minus B is 0, B is T of A. B is semi-simple. And especially each isomorphism between two commutative semi-simple Banach algebra is a homomorphism, because we can use again for the converse this theorem. And if we have a commutative semi-simple Banach algebra, all complete algebraic norms are equivalent. And it's interesting because with putting some algebraic condition like semi-simplicity, we can make a very nice result concerning topological structure, and we can say that all complete algebraic structures are equivalent. And it's, of course, and the thing I told you, it's just a special case of Johnson theorem, which is really famous theorem in automatic continuity theory. Yes, it's really interesting, but just I told you this result in orally because maybe I don't because I want to start Banach function algebras. In the rest, X is a compact Hausdorff space. Okay. But before saying Banach algebras, I just mentioned something about Gelfand transform. I like to, because I want to use it in here, of course, just as a remark or small preposition. Just before Banach function, just please add this part. The Gelfand transform. I want to say that we know that Gelfand transform is norm decreasing because as you see in that theorem, um, it's norm decreasing because supremum norm of A hat is at most supremum norm of A. I want to say that when Gelfand transform is an isometry, I mean that when for each A, norm of A is is a supremum norm of A hat. The Gelfand transform is an isometry or is isometric if and only if for each A we have this one. Of course, because of submultiplicativity, it at most norm of norm of A squared. For proof, if isometry, it means that A in A, we have norm of A, supreme norm of A hat is norm of A, norm of A. And so norm of A2 is from this, for example, it's norm of this. We know hat is a homomorphism, so we can write it hat power 2. And for supremum norm, we have this one. And again, we use this one, and we obtain the result. For the converse of so it's trivial. By induction, let's A in A. We know that norm of A power 2 is norm of A power 2. And then by induction, we can say that norm of A to N is equal to norm of A power 2 power N. And then norm of A is norm of A to N 1 over 2N. Just take a limit. This is exactly subsequence of the sequence I mentioned in the formula for spectral radius is subsequence, and so the limit is exactly spectral radius. And now Banach function, algebras. What, I just missed this. Okay. First of all, definition of algebra, and X is a compact Hausdorff space. X is compact Hausdorff space. First of all, definition of function algebra. A subalgebra A of C of X is called a function algebra on X if A contains the constant functions. Contains the constants. And also, A separates the points of X means that for each distinct 2 points, for each distinct 2 points like X and Y in X with X is not Y, there exists F as usual, separate the points, such that F of X is not equal to F of Y. And if function algebra is a Banach algebra with respect to a norm, we call it Banach function algebra. And there exists a nice relation between commutative Banach algebras and Banach function algebras with the aid of Gelfand representation theorem, which makes just consider subalgebras of continuous functions. We know these objects better, and the operations between them we know much better. Anyway, and a Banach function algebra on X is a function algebra on X, which is a Banach algebra with respect to a norm, which is a Banach algebra with a norm. If this norm is the sup norm or uniform norm, we call it uniform algebra. So a uniform algebra on X is the function algebra on X, which is uniformly closed. For example, our example, C of X, the uniform algebras. This algebra AD is a uniform algebra because the norm is supreme norm. C, and they separate the points, of course. C of X, because of Orison lemma, it separates the points. This algebra, because you have inclusion map. Z of alpha is alpha. So separate the points, and of course it contains constant. Or for example, for Cn, it's easy to see that it's separate the points. You can define suitable function. For Lipschitz algebra, of course, because for example, f of t as a t of x, t of the distance of t and x at x is 1, at x is 0, and the other points is not 0. So it separates the points. So there are Banach function algebras, disk algebra, C of x, uniform algebras. But for example, Cn and lip of x, Banach function algebra, because their node weren't subnode. Banach function algebra. And all of them contain the constant and separate the points. And two notation, of course, we had it before, I think, z of f, of course, for example, for each in f of x, z of f, it means f inverse of 0, which is closed subset of x, and co-zero set of f, it means the complement of this one, which is an open subset. Um, let's say a proposition. Actually, when we have a function algebra, I want to say that the topology of X is the weak topology induced by A. I don't know where, here. Actually, the weak topology induced by A, I mean that the weakest topology which make each F in A continuous is A topology, and A topology is the coincides with a given topology of X. So the weak topology on X induced by A, or sometimes it is called A topology. And I told you it's the weakest topology which make HF in A continuous. Is okay, coincides or agrees with the original topology of X. Of course, we know that each A is a subalgebra of C of X, so each function here is continuous with respect to the original topology of X, and this is the weakest one. So it's clear that let's denote it by tau of A, and the original topology with tau. So because each function is continuous with respect to tau, and this is the weakest one. So clearly, tau A is weaker than A. For the converse, if for the converse inclusion, if if it's not true, tau, it's tau. If tau is not a subset of tau of A, then according to the definition of tau topology, and then there is a net like X alpha in X such that X alpha goes to X in X with tau A topology, but not in the original topology of A. But not such as this, and X alpha doesn't go to with so it's so since X alpha doesn't go to X in tau topology, it means that so there exists a subnet like X alpha I doesn't go to X. And since X is compact, we can say that, but there exists a convergent sequence for so convergent subnet for X alpha. But the limit definitely is not X. So since X is compact, there exists a subnet X alpha I of X alpha such that X alpha I goes to Y, which is not equal to X. Then for each F in A, because of this convergence, we have F of X alpha goes to F of X because of this convergence. And on the other hand, each F is continuous with the original topology because it's subset of C of X, then F of X alpha I goes to F of Y. Anyway, this is a subnet of this one. And then the limit should be unique. F of X is equal to F of Y. It happens for each F, but we know that A is a function algebraic separate the points, so it should be Y, but it's not true. It is a contradiction, shows that the converse is also true. It means that tau is a subset of tau A. And let's continue with this part. And let's, I want to characterize all elements in the character space of C of X. In other words, maximal ideal space of C of X. But before I say a definition, and then I do it. Let's A be a function algebra on X for each X we define a homomorphism and we call it the evaluation homomorphism at X is this map, is delta X from A to C. We take delta X of F to F of X. Because we have pointwise operation, it's clear that it is a homomorphism. And the second part, if A is a Banach function algebra, delta X in M of A, because this is a homomorphism. And I just define M of A for Banach algebra. That's why I put it here, Banach. And the map I from X to M of A, which takes X to delta X, is a continuous surjection. No, surjection. Yes, no. Injection. Yes, this is just for all general algebras, not but for C of X. For C of X, of course, surjection. It's injective because A separate the points. If, for example, delta X and delta X prime is the same, it means that for each F in A, F of X is F of X prime, so is X prime. So it's injective. Continuity also, it's easy. For example, if X alpha goes to X, then for each F, because F is continuous, F of X alpha goes to F of X. In other words, this is delta X of F, and this one, delta X of X alpha of F, and this is delta X of F. And according to Gelfand topology or Bbb topology, it means that delta X alpha goes to delta X. So it is continuous, always. And not necessarily, of course, surjective, but if it's surjective, we call our Banach algebra is natural. Which is important definition in functional algebras. A Banach algebra is called a Banach functional algebra. A and X is called natural if M of A is X. In other words, I mean that if the I map is surjective, means that I map from X to M of A, X to delta X is surjective. Of course, it's surjective, if also continuous, injective, and because it's compact, it's Hausdorff, and surjectivity, we can say that equivalently I is homomorphism. because I told you this is injective, and because of subjectivity, compactness, the converse from topologies, also continuous. I want to say that as the first example, C of x is natural, and so M of x is just evaluation homomorphism. C of x is natural. I mean that I want to say that I is subjective. Okay. If it's not true for contradiction, we assume that I is not subjective. And so there exists phi in M of A such that it's not in the range of I. So for each x, phi is not the form of delta x. And I told you, when we have two characters with the same kernels, they should be the same. When they are different, it means that the kernel is different. So there exists f, which is maybe related to x, such that phi of f at x is 0, but f of x at x is not 0. X is a subset of co-zero set of f of x. We know that they are open. X is compact. Each open cover has a finite subcover, and then X is compact, and then there exists x1, xn in X, such that X is a subset of co-zero set of f of xi, I from 1 to n. And now we define a useful function as follows. We define G as the f of x, summation of f of xi, f of xi bar. This is complex conjugation in here and then in complex field. Which is in C of x, continuous because all of them continuous. And for each x, if x in x, then there exists one index such that f of xi at x is not 0. And with this multiplication, one of these elements is strictly greater than 0. Anyway, it works for each x, and we have g of x is positive, strictly positive. It means, and 0 set of g so is empty. And when 0 set is empty, the inverse is we have the inverse of g, because if we have continuous function with empty 0 set, 1 over g is well defined. And from the second star theorem, when we have invertible element for each phi in character space, that this element should be non-zero. So phi of g is non-zero. But on the other hand, we have phi of g, phi is phi of f of xi, phi of f of xi bar. Okay. And phi of xi is 0. And then this summation is 0. This contradiction shows that no, we have surjectivity. So M of C of X is natural. Sorry, C of X is natural. M of C of X is just X. Just I have 10 minutes time, and then I want to say something and then leave it as an exercise, and which is theorem, of course. And we use two properties of C of X. The first one is closed under conjugation. And the second one, when the zero set is empty, the function is invertible. It works for each Banach functional algebras, which have these two properties, self-adjoint, and also with zero set empty, we had invertibility. Okay, let A, and the proof is also similar. Be a self-adjoint function algebra on X, then A is natural if and only if 1 over F is in A whenever F in A with zero set empty. And self-adjoint, I mean that if F in A, then F bar is in A. Conjugation is also in A. Okay, this part is really easy, and the second part and the converse is also like this. Just it's enough to change C of X to A, nothing more, and I just leave it as an exercise. But this part is it's really easy. So let me prove it. If F in A, with I want to show that if it's natural and self-adjoint, we have this property. With Z of F is empty, it's actually the second star theorem. Then since A is natural, it follows that for each phi in M of A, F is not 0. Because phi of A just the evaluation homomorphism, I mean delta X, and the range of F, which is not 0. And so from the third part of this star theorem, we can say that F is invertible. And so F is invertible. And please. And just I mimicked this proof and then nothing more. You have everything. Okay, just finish now. And many thanks for coming. And I hope to see you tomorrow and for the last session, I think. Thank you so much.